we're trying to motivate you into understanding why we need transformations. Example 1, calculate the double integral over region T of dA, where D is the region shown below. When they talk about double integral without an integrand, they mean integrand is 1. The next thing is that double integral of 1 dA is going to be equal to the area D. The first attempt to compute this area, basically what we see is that the region is not simple. Therefore, I have to divide it into multiple simple regions, and it takes a lot of work basically. And then the square root will show up, and so on and so forth. So it becomes very complicated. You may at this point want to suggest, why not use polar coordinates? Have x be r cosine theta, y be r sine theta. Then here r obviously goes from 1 to 2. And theta goes from 0 to down here, which is 3 pi half. So according to that, should I compute the area? Is area of this region the double integral from 1 to 2 dr from 0 to 3 pi half d theta. And if you compute this, the most inner integral is going to be 2 minus 1, which is 1, 0 to 3 pi half d theta. So this part ends up to be equal to 1. And then the outer integral is going to be 3 pi half. Is this the area? Turns out to be not true. And here is what we see. So this is the region that we're trying to find the area. That's the integral that we wrote from 1 to 2 dr 0 3 pi half d theta, which was equal to 3 pi half. And you can see that is exactly equal to a rectangle that r is between 1 and 2, and theta is between 0 and 3 pi half. So it's equal to that area. So is this actually equal to area of this region? And area of this region, the easier way to compute this is to find the entire area of the 3/4 of a disk of radius 2, then subtract this empty 3/4 of a disk. 3/4 of pi 1 to power 2, and that is 3/4 of pi 4 minus 1, or 9 pi 4th. And the two of them are not equal to each other. So transformation basically is a function that takes every point and to another point in the two-dimensional space at this when we're using transformations in two-dimensional space. It has a couple more properties, and especially for this course, we consider specific properties. But here you can see that r cosine theta and r sine theta for x and y takes every point in r and theta space into x and y space. But the integration over this region didn't give me the area over here. The reason for that, pictorial reason, again, motivating examples, is this. When you're looking at r and theta region, every little rectangle here, I chose a rectangle that is between theta is between pi 8 and pi 4. The first rectangle is for S1, R is between 1, and for S1, R is between 1 and 2. For S2, R is between 3 and 4. So for S1, I'm going to go to where radius is 1 and 2. Here is 1 and 2. And then here is pi 8. And here is pi 4. And so this region is going to go into here. Now for S2, again, I'm between pi 8 and pi 4, but the radius is between 3 and 4. So S2 basically moves over here. So depending on how radius is, the area is changing. How big the starting radius is, the area is changing. Even though the difference between the two radius here, 2 minus 1 is 1, 4 minus 3 is 1, and theta beginning and end for both of them are the same. Because the starting radius is bigger, you get a bigger piece over here. So now what we want to do next is to make sure that basically consider that when we're considering this integral, basically. Consider that when we're integrating over dr d theta.